All right, please welcome Nico Méndez from Open Lab Automata.
Thank you. Thank you. Thank you, team, for organizing. So today I will share a few updates on the Open Lab Automata project. There are many things going on, but I try to pick the most important ones, and we can talk about, I can elaborate on the aspects you might be interested in. So previously, about 2 years ago, I talked about the MK3 machine. It's like a robot, a tube changing robot based on aluminum extrusions and basic Cartesian kinematics. And at the time, we only had an adapter for to P200 micropipette, which also we worked with 2 years ago at Seattle. We did a little teardown of the OT2 micropipette and realized it wasn't too sophisticated, so we were so we didn't feel too bad about ours. I also showed that there was a basic backend to drive the MK3 with Pilot Robot, and some documentation we made in MK docs. And now we will talk about some updates on this. So there are a few minor revisions on the MK3 machine, making it easier to assemble and manufacture. We have tested our own multi-tip micropipette, and there are some more tools I will briefly show. I will talk briefly also about volumetric calibration and why this is what we actually sell. There's also a basic machine class for Science Jubilee, which was pending since our visit to POSE. And we also made a new documentation website for open hardware projects called Stepwise Docs, and I will show briefly also that. On the hardware side, here's let me see if I can, turn on the lazy port there. So here's our pipette. It has a multi-stage tip to fit different kinds of tips. And because ejection was complicated, we just crash into this thing in a controlled manner to remove the tips. It's like a fork situation there. We also reproduced Julie's touch probe tool. This is a very nice tool. I mean, it's very precise. So for measuring things, it is great. Not so useful for lab automation, perhaps, at the moment, but still cool. We also made a little dyno camera microscope, also based on the Jubilee design, and this is the new gripper, which I'm just barely finished testing yesterday. But it's a very nice design as well, very simple, just a motor, a single pulley, and instead of 3D printing the belts themselves, I just glued the belts on the underside of the linear rails here, and of course the linear rails, which are the most expensive part. But I'll show other attempts at this, which were much cheaper, because these linear rails are hard to get, also quite expensive. And there's also there's also been a lot of work on equipment, like this small optical density meter or absorbance meter, which we haven't integrated with the robot, but we'll talk about that later. Another news, the first news, perhaps this is the rose part. We are making robots for people, and we have received requests also for an incubator module for well plates, both hot and cold. The gripper I just showed also goes to one of our customers, and people have been asking for a multi-channel pipette for a while now, but perhaps we can unlock this year or the next one, depending on timings. I am very slow to work, so it might take a while. So this is about what we're actually selling part. When you make a micropipette out of a CNC machine, and you get a tip holder, and you put a piston in it, and you start pipetting, and you actuate it with a robot, what you get for serial dispensing is actually doesn't look like a straight line. So at first you under dispense then you over dispense slightly, and then you under dispense at the end again. So this is what we are actually trying to correct for and sell, because making pipettes all in all is a very simple thing, but the actual value that we offer and that anyone offers really when selling in scientific equipment is that it is calibrated to something, to some degree, and you can rely on this tool. But there's a second step to this also, which is what we are working on right now, which is a way to make it to integrate the calibration step into the very robot, so you can recalibrate your pipettes in the same of the machine in case you think it's not working anymore, because there's still, this is like one of the last barriers to adopting an open hardware micropipette tool, because who will calibrate it for you? So you have Gilson services, Eppendorf services, and I don't know, Sartorius, I don't know how many brands make pipettes, but most of them, the established ones, have a calibration service somewhere. I mean, we have them in Argentina, I guess. In the US and Europe, this is also very common to find, easy to find.
And
so
they're
we
third
are,
party.
Third party, right?
Yeah.
And so we made this little device that works essentially like a Neubauer chamber. These are little wells with well-defined and precise offsets between the base part and the top surface, let's say. These are inverted. So you place your little drops there. You place a treated glass slide, microscopy slide that has been treated with hydrophobic coating on the other side. You place it on top, and you do dimensional reduction to those drops, and now you can measure very accurately how much or how badly the robot is pipetting. And then I've not shown this because it's a very, I will not show this because it's a prototype my cousin is working on. He also has a robot. And you just tell a large language model to interact with our software stack and tell it, okay, put drops here, image them, measure them, and then tweak the calibration parameters that the tool accepts until you get a straight line here and report the results. So if you can do that, it's not even Bayesian optimization or any of those kind of fancy methods. No, the LLM just figures it out on its own. And it's pretty cool because now in the very robot that you got, you have the calibration built in, and you don't need any additional service. And this will also work for any pipette as well. Any questions about this?
I'm curious about the LLM usage. So are you just using one of the commercial models? So it talks to
Yes.
Claude or OpenAI or whatever, and it
We
has
are
to have an internet
prototyping
connection.
we are prototyping with GPT.
Okay.
And it works.
And then is it pretty consistent? I mean, this feels like the kind of thing where it could be, but I just like the outputs, because the whole thing with the LLMs is that they have a degree of probability built in, but they're able to sort of cross-check themselves and the calibration is consistent.
Right. So we have over here, not over here, but somewhere, there's a calibration document with the sequence of steps and the tools you have to use and the parameters you have to tweak and what they do. So you give those as context. And then there are a few MCP. There's one simple MCP server that lets it run a protocol, and it returns the results. And yeah, the sequence is pretty simple, so it can follow. You can take conclusions very easily based on that. So perhaps it says, oh, I see the first drop is under dispensing. The docs say that I should tweak this first. So it tweaks it a little bit up, and then runs again. It runs again the calibration procedure, and it eventually reaches an acceptable error rate and finishes.
Cool. That's cool.
Yeah, it was easy, right? So it's also an example of the self-driving lab. Now it's a self-calibrating pipette. You have to use for this, of course, the gripper to move the glass slide and the camera to take pictures. But we are trying to work on alternative ways of using it without those things. Of course, you can operate it by hand, but perhaps the pictures can be taken with a cell phone or something else. We have found
Nico,
that the main, yeah.
one question like if you look at the like you have a really broad volume capacity for this pipette, like is the calibration primarily problematic in the low volume range, or is it equally like you have to calibrate at all volume ranges, or?
Yeah, so here this prototype device has 3 volume ranges. So the slots here are different depth. This is for the microliter range. This is for the, I don't know, 20 microliter range, and this for the 200 or a bit more microliter range. You can imagine making these larger, and you can squish the drops more in a larger device to be able to quantify its area more accurately. But I don't have like a good answer for this. But yeah, the most sensitive part of the device is this part, in which the gap between the Teflon substrate and the coated glass slide is about 200 microns. And we have calculated it to be able to resolve about 0.02 microliters, in theory at least, given some camera resolution and magnification and other parameters. And it sort of works, but it depends a lot on the segmentation algorithm we are using, because if they are not exactly round, OpenCV struggles with that a little bit. We have been starting to use the segment anything model, the AI model by Meta, I think, to segment the drops, and that works really well. But yeah, that is the most problematic part.
For the Jubilee hackathon, I think Tim wrote some code that does some of this as well, but we should sync up about it for sure.
Yeah, I was very curious to see what you did with the drops. I'll ask for some more pictures later on, because the method you used to illuminate the drops was very interesting, and perhaps it can be applied here as well. For now,
I'll
it's
try
just
on that prototype. I got it downstairs, and I don't know if I can do it right now, but yeah, later today.
No, don't worry. Yeah, sure. And well, I think this is a great thing, because it's a very simple. You can machine this very easily. You can have this manufactured by JLC PCB or JLC CNC PCB way and so on, or just do it yourself. But then it's an early prototype. It probably won't look like this in the future. And yeah, that's about the hardware. So I wanted to mention that now I am trying to mill my own tip holders, which is the other thing that is hard to do. I bought a $100 manual CNC from China, and then added motors to it, and now it does CNC. Because this project is mostly about decoupling the automation hardware from academia and well-funded industry in general, right? To be able to do the things without needing to, do a PhD or get into or having a cousin that operates a large milling machine. So everyone can access this tech from entering at some point. Then on the documentation side, this is the new site Facundo made. It's called Stepwise Docs. There are a few projects there, including the robot and our pipette. There are some ramblings about metal casting with microwaves, which I will talk about shortly. And other people are also adding their projects here. It's a very nice, very simple to use app. There's the Transilluminator project, which uses this PCB that just arrived. And here is an example of what a guide looks like. So we have all the guides here with all their steps, and steps look like this, very similar to iFixit. And yeah, we're trying to rely more on this. And we think it's probably the best way to document stuff is to do iFixit style guides. This also has a bill of materials and also integrates with ChatGPT, which automatically reads the pictures you pasted on the step and generates the instructions for what you're doing, which is quite crazy, actually. Because normally ChatGPT is very bad at spatial and mechanic things because it has no idea that the world exists in three dimensions. But it was pretty accurate in the instructions it generated, and they work as a boilerplate really well. You just review them, and it reduces a lot the amount of work you have to do to document something, as long as the pictures are good, right? That's about the documentation. And now this is more like the bad side of OLA. So last month I went to Parque Natural Caruquinca, which is here. You can see if you look at Earth from this side, there's not much else except South America and Antarctica. So it's really far away. And the idea was to test a molecular biology kit that uses open hardware and open regions made on site. So that means that the enzymes we used were expressed, were purified on site here in a place where there was no biolab at all. We just brought the stuff and did it, and it worked really well. And what is interesting about this initiative is the molecular biology kit itself and how it could be integrated into automation. So it can be used as regular lab hardware, and how it can be used by a robot at the same time without having to have two different versions of the equipment, one automation ready and one for humans. So there's a centrifuge that is thought that I designed it to make it compatible with a robot. There's the Pocket PCR, which can be used autonomously if you, instead of capping the tubes, you just put mineral oil as the old thermocyclers did, and then the PCR reaction just goes on, and you can pipette the end result directly without having to move the tubes. There are some colorimeters which are for now not compatible with a robot, and electrophoresis things. So it would be really nice if the robot could now seed the electrophoresis gel with samples. It has a much better stable hands than I do. And there's also these devices, which are pretty cool. There are the thermal cyclers I mentioned. There's a new open hardware thermal cycler for quantitative PCR, and there's the Qubite for quantitative LAMP. And these will be awesome to integrate into the robot, right? So the idea here is to try to get everything connected, at least to some degree, in order to have an open ecosystem for the automation from end to end, from making your own tips in a CNC lathe to using the reagents you just synthesize to detect something in some water sample or blood sample or whatever. And this is I have shown this before, and I updated it a little bit. This is my perception of what the open lab automation universe looks like. And so you have here what humans do: pencil, paper, brains, and hands. The lab notebook is the graphic protocol writing part. You have data support on paper, and you define your protocols on paper, and then you just execute them. And then there's the open runs stack, which has an protocol designer, stores in JSON, has its own API, and works on open electronics. There's the PLR part, which is mostly just the programming interface here, and then it's connected to a lot of expensive black boxes by Tick and Hamilton and friends. And there's our stack here, which doesn't offer a Python API, but instead connects to either PLR or Science Jubilee to offer that kind of frontend. because to not reinvent the wheel, of course. And there's all of these things. One thing I noted in this part is that I think it's important that we have, that this technology stack is data-centric and not API-centric as it is currently, because data is the only common language that really every machine will understand. So I think it's necessary that we start, thinking for all of this ecosystem and integration things. We need to agree on having data-backed software that stores information and state persistently in a shared database, and that can be consumed by anyone or anything without having to make a pull request to Pilot Robot or Science Jubilee to get some information that is not available through certain versions of the Python libraries. There's also Ivory OS and friends here that sort of, I don't know, I didn't know where to fit them really, because they sort of consume these Python APIs and make a graphical way of running them, which is cool. And also, I don't know where AI goes into this, but probably will consume all of the resources here and the backends of the graphical applications to stuff. But the MCPs are missing. And then some upcoming things.
I've got a question,
This is also
Nico, if
something.
that's all right.
Yeah, what? Sorry?
I was just curious about so I completely agree about the sort of data-centric approach. Some sort of descriptive language that can be sort of stored in a database or emailed seems extremely important. And I always balk when people invent their own sort of Python-like thing. When I'm like, JSON's right there, just put it in data,
Yeah.
Have you written about or sort of published your approach to using JSON? Because I mean the process for actual interoperability on that kind of data is often, hey, well, yeah, but you think of the world as being plate centric, and I think of it as being, whatever, Flask centric. And so there's a lot of sort of discussion that could be had there. Are those discussions you're having, or you just kind of doing your thing?
No, I had, well, when I tried to implement the Ola backend for Pilot Robot, I had lots of these discussions with Rick. I
Yeah.
think we burnt out each
Yeah.
other. But I think this can be resolved because it's not so different. You have like this idea of a container that exists somewhere with a solution. And also in chemistry, you have more chemistry application. You do solid handling. So I've been told it's very hard to do, but there's also that concept. So I think it's mostly about agreeing to build bridges than how to represent the data. So we need to build bridges between our software, and we want data to be the middleman, and that data must have a schema and a data schema and a version, which can be a JSON schema, and then it would be possible to just have one version of the schema written into the JSON data, and have programs understand that JSON abstraction, and if they don't have enough data or have the wrong data, they will just error out. So the idea is to put the data there and then let the libraries consume them however they want. If you want to be plate-centric, be plate-centric, but don't mess with the schema. The information has to be there, that's all.
Just sorry, one more question on that. How or where are those conversations happening? Do you know? Is there like a GitHub repo? Or?
In my conversation with Rick was a few years ago, I think. And it was in the Pilot Robot forum.
Oh, makes sense.
A rather long thread. Yeah. So I also tried to, in the first instance, I tried to integrate the OT software stack, which is open with, make an arrow that goes from here onto the pipetting bot. But they didn't want to work on that. So obviously, right, because they want the robot with their stuff. and they want to make as much money as possible. I believe they saw this idea as a threat more than as a good collaboration, desirable thing.
Yeah.
I think a few arrows here might be new. Well, I mentioned that I wrote a machine adapter for Science Jubilee. So in theory, you could enter Science Jubilee with an OT definition of Flower and then end up using the pipetting bot. The tools are interoperable as well, the ones I showed. They have the same kinematic mount, and you just have to switch the wedge plate, which I 3D print. And then Jubilee's one is machined. So I try to simplify that a bit. I'm not saying it's better, probably not, but I can make it. So I prioritize that. Well, any more questions about this? 1, 2, 3. Okay, so upcoming things is just a few random things I'm beginning to be interested in. So I just mentioned that this idea of the no-water chamber for pipette calibration, but there's a perhaps more general thing, which is, I don't know how to say this, how the official name of the technique is, but you can sort of do droplet handling. So here in this, we are seeing here in this image what is in this little slide. That is a sandwich of glass, non-polar fluid, and then another glass slide. The bottom glass slide has electrodes on it, and when you input an aqueous solution into this, you can sort of move it around, like it is done with the open drop, but this is a much smaller scale. So it's like liquid handling, but with droplets. It's a very cool thing to do lots of high throughput combinations of conditions in a very tiny space, because this device is capable of splitting the droplets, and by imaging them, you can get their size, or how much volume or quantity of something there is in each droplet, and it's good for many assays using very little volume. Another thing we are working on a few things with NASA as well. So we are working on this idea of a tile-level small robot that you can sort of paste next to each other, and in that way chain small robots into a larger robot. And this would be very nice as well, because it's less intimidating to build, smaller in footprint, and also easier to extend. So probably the MK4 we have this smaller shape, and well, that's if we get we applied to NASA applied to us as long grant, and if we get that, we could possibly work on this and get to something nice. And then there's also, this is the next version of the gripper. Actually, the previous one had also a rotary axis here, so I thought about, I was trying to implement something that can remove caps from tubes by turning in this direction. But 3D printing everything didn't work. I always think it will work, and then it doesn't. So it was very wobbly. But I will come back to this once I finish my integration with the basic gripper I made with the linear rails. And also, I'm trying to get rid of a really big dependency with CNC machining and milling. And I've been experimented with metal casting at home with microwaves, which is very fun. And with that, I made all of the pulleys I required to convert my small lathe to a CNC machine and to make the tip holders. So I'm trying to cut all of the dependencies with the more well-established with the establishment of things. I don't know how to say it. That you don't have to be a scientist to access something. That you don't have to be an automation engineer to get a machine. That you don't have to have a metalworking workshop to do your machines. So trying to make everything more accessible for one. Of course, I didn't develop this method. Most of the things I just stole from the internet. But I think it's also interesting. Perhaps next time I will bring sort of like a tech tree, and that to show how many of the things you still need to be part of, in the usual in the usual traditional way of having a large workshop or being part of a large lab to do stuff. I don't know if I could explain it. I think I got lost in how to say it. And this is really fun. You should try it. And I think that's it.
How do you get the microwave generator? Like what?
From a microwave.
What is it?
Yeah.
A regular microwave.
Yeah. So you get a microwave, and you don't have to do anything with it. You just use it as it is. You make a crucible out of silicon carbide and water glass. You make this with things you can have at home other than the water glass and the silicon carbide. And then you sort of cook it and cure it inside the microwave oven. This thing heats up really well, absorbs microwaves really well. And to get the temperatures up, up to melting, copper, aluminum, and in some cases also steel, you have to wrap this around in a ceramic fiber blanket. So the energy, which is transparent to microwave, so the energy accumulates in the absorbing element, which is the crucible itself, and the heat does not get out because the fiber blanket is very good at insulating heat.
That's really cool. I have a different application I would like to use this approach for. Like the students have that I was mentioning at the beginning. They're making sol gel particles, and like one of the teams as catalyst supports, and they need to undergo a calcination step, which is extremely time dependent. So it would be awesome to have a well plate compatible crucible like material where they could calcinate all of their samples simultaneously.
Yeah, I have no idea how that could be done, but of course, what you can do is, instead of using a crucible, you can make a heating element and put it inside the ceramic fiber blanket, and then inside you have space to put any vase or any container you want to put.
I was just thinking that could you make like a well plate like structure out of the same water glass silicon carbide mixture? So it's, instead of a crucible, you make it have the dimensions of the well plates. So you deposit directly into that. Yeah.
I think you will have the answer for that, but I can tell you straight away that it's the resulting crucible is very porous, has a very high porosity. So anything that is minimally liquid will just get in there into the structure and pour out. It's basically a filter for water and a crucible for molten metal.
I see.
But I'm sure it can be done in some way. I mean, I have no idea. I have been researching a lot to get this to work, but I'm sure a certain someone with chemistry education will know how to do it better. Well, this is it, I think.
Nice. All right. Well, let's thank Nico. Thank you, Nico.
No, thank you for listening.